welcome to the deep dive. We're taking a look at probabilistic causation today. It's a way of thinking about cause and effect that might just shake up how you view the world, especially if you're a philosopher.
It's really fascinating how probabilistic causation moves us away from this strict idea that every cause always leads to a specific effect.
Yeah, the real world's a lot messier than that, right? It's more like smoking makes lung cancer more likely, not smoking equals guaranteed lung cancer.
Exactly. It embraces the uncertainty. It says, hey, sometimes things happen, sometimes they don't.
So for our listener, maybe someone deep in philosophical thought right now, how does this probabilistic view change the game for understanding cause and effect?
Well, it really challenges those traditional regularity theories, the ones that say a cause must always be followed by its effect. But think about it. You could have something happening consistently before something else, but it doesn't mean it's the actual cause.
Right, right, like that example we talked about before with the witch doctor and the hexed salt dissolving in water.
Exactly that. Just because the salt dissolves after the ritual doesn't mean the ritual made it dissolve.
Okay, so how does probabilistic causation help us avoid these kinds of mix-ups?
It shifts the focus. Instead of looking at whether a cause always leads to an effect, it looks at how a cause changes the probability of the effect happening. So instead of saying A always causes B, we'd say A increases the chances of B.
I see, so it's not about a guaranteed connection, but more about understanding the influence, like a cause nudging the odds in a certain direction.
Exactly, and this whole idea of probability raising is really at the heart of probabilistic causation. But to really see how powerful it is, we need to look at this concept called screening off.
Ooh, screening off. That sounds interesting. Tell me more.
Okay, imagine you have something, we'll call it C, and knowing C gives you all the information you need about something else. Let's call it E. Now, if there's another factor, A, that's related to E in some way, it becomes kind of irrelevant because C has essentially screened it off.
So C is like a gatekeeper of information. If we know C, A doesn't really matter anymore, even if it's connected to E.
Exactly. Like, think about HIV and AIDS. Unprotected sex can lead to HIV, and HIV leads to AIDS. But once you know someone has HIV, the way they got it, like whether it was unprotected sex or something else, doesn't really change their chances of developing AIDS.
I get it. So knowing they have HIV kind of screams off those earlier factors. It makes them less relevant to the outcome. It's like focusing on the most direct cause, right?
Exactly. Okay, so let's shift gears a little bit and talk about another cool idea, conjunctive forks. It helps us figure out the direction of causation.
Conjunctive forks. Should I be drawing a diagram for this?
Well, picture a fork, right? The handle is the common cause, let's call it C. Then the two prongs are the events that are correlated because of C. Let's call those A and B. Now, Reichenbach, the guy who came up with this, said that with open conjunctive forks, these are forks where there isn't some later event causing both A and B. We can actually trace the flow of time. We can see how things move from cause to effect.
Okay, so we're following the path from the handle of the fork, the cause, out to the two prongs, the effects. But you said earlier we'd revisit this idea. Is there a catch?
Well, conjunctive forks aren't always a foolproof way to figure out causal direction. There are other things that can make it tricky. We'll get to those a bit later. But first, let's tackle something called Simpson's paradox. It's a bit of a brain teaser.
Simpson's paradox. Yeah, I've heard of it. Isn't it kind of like a statistical illusion?
You could say that. Imagine you're at a philosophy conference and you notice that more men seem to be accepted as presenters than women. But then you look at the individual subfields, ethics, logic, metaphysics, and within each field, women actually have higher acceptance rates.
Hold on, how is that even possible? It seems like it's contradicting itself.
It's not really a contradiction, but it shows how hidden variables can really mess with the overall picture. What might be happening is, say, way more men applied to a logic track that's super competitive, dragging down the overall acceptance rate for men.
Ah, I see. So even if a cause seems to make something less likely overall, it could actually be making it more likely within specific groups. It's a reminder to look deeper, right?
Exactly. Don't just take the surface level numbers at face value. That's where causal modeling comes in. It's a more sophisticated way to map out these complex relationships.
Okay, so let's model some cause and effect. How do we get started?
So instead of just observing if something makes something else more likely, causal modeling creates a visual representation of how different things are causally connected. Think of it like a diagram with arrows showing those causal links. We call these directed acyclic graphs, or DAGAGs.
Oh, like a flipchart for causation. I can see how that would be really helpful in sorting out those messy real-world scenarios.
And it gets even more sophisticated. We can use what are called ADMGs, which stands for acyclic directed mixed graphs. These can represent those hidden common causes, the things we can't directly observe, but that might be influencing the whole system.
It's like those behind-the-scenes factors pulling the strings. I bet our philosopher listeners really intrigued by this. How does causal modeling connect to philosophical questions?
It offers a much deeper, more nuanced way of understanding cause and effect, especially with its ability to handle those hidden variables. It can shed light on situations where traditional philosophical approaches might struggle.
Okay, so we've got these fancy diagrams, but what are the rules of the game? What assumptions do we make when building these causal models?
Great question. One of the most important assumptions is the Markov condition. This basically says that once you know the direct causes of something, looking back further in the causal chain doesn't give you any new information.
So if we know that sunlight, water, and nutrients cause a plant to grow, knowing what the weather was like a month ago doesn't really matter.
Precisely. The Markov condition helps us keep things simple by focusing on the most immediate causal links. Then we also have the minimality and faithfulness conditions. Minimality ensures we're using the simplest model possible, and faithfulness says that any independence we see in the data reflects a genuine lack of connection, not just some random fluke.
So we're keeping things tidy with minimality and trusting that our data isn't tricking us with faithfulness. But even with all this, can we be truly certain about causation just by looking at probabilities?
That's a crucial point, and it's a good spot for us to pause for now. Even with these sophisticated models, there are limits to what we can learn about causation from probabilities alone.
Sounds like there's still some mystery to be uncovered. We'll definitely have to pick up this thread in part 2 of our deep dive.
Picking up where we left off, we should look at some places where causal modeling might not be the most reliable guide.
Yeah, you mentioned something about canceling causal pathways last time. What exactly does that mean?
Imagine a gene that actually helps cells grow, but it also, at the same time, suppresses another gene that would normally stop cell growth.
Oh, interesting.
So the end result might be that you see no noticeable change in cell growth, even though that first gene is busy doing stuff behind the scenes.
So it would look like that gene isn't having any effect, even though it actually is.
Exactly, and that's where just blindly applying that faithfulness condition could really mislead us.
Yeah, we might think, oh, no causal relationship here, but there's actually a whole lot going on.
Yeah, it's more complicated than it looks, and this whole thing gets even more tricky when you start dealing with systems that have feedback loops.
Feedback loops. So, like, where a cause can end up influencing itself through a whole chain of effects.
That's it. It's like a cause and effect boomerang.
How do you even begin to untangle that and figure out what the original cause was?
Well, it can be a real challenge. And then on top of that, you have to remember those unobserved variables we were talking about earlier.
Right, those hidden confounders.
Exactly. They can really mess with our interpretations of what's causing what.
It's like trying to solve a puzzle with missing pieces.
It kind of is. So are we just stuck in the dark when it comes to these hidden variables? Not
Okay,
necessarily.
it's good.
We can use our knowledge of the specific area we're studying and really think through those potential confounders. It's kind of like being a detective, you know?
Gather the clues, piece together the most likely story.
Exactly. Context is everything. We can't just focus on the numbers in isolation.
So, are there any tools or techniques that can help us deal with this uncertainty, especially when those unobserved variables are lurking about?
One thing we can do is use a technique called sensitivity analysis. It basically lets us see how solid our conclusions are, even if there are these hidden confounders affecting things.
It's like we're stress testing our models.
Yeah, we're asking, what if there were unmeasured variables messing with things? Would our results still hold up?
It sounds like probabilistic causation really brings a lot of uncertainty to the table. Does that mean we can never really know for sure about cause and effect? Are we just stuck with probabilities and possibilities?
Well, that's a question that philosophers have been debating for centuries. But I don't think probabilistic causation means the end of causal knowledge.
Okay, good to know.
It's more like it refines our understanding of cause and effect. It helps us see that the world is inherently complex and uncertain.
So not causality is dead, but causality is more complicated than we thought.
Exactly. It's a call to move away from those overly simplistic, deterministic views and embrace something more nuanced. And that shift in perspective has really big implications for how we think about ethics, law, public policy, all sorts of things.
Okay, let's dive into those implications. How does probabilistic causation change our approach to moral responsibility, for example? Especially for our philosopher listener out there who's thinking about how humans make choices.
If most causes only increase the probability of something happening and don't guarantee it, it raises questions about how much we can hold people responsible for the consequences of their actions, right?
Right, it's like you can lead a horse to water, but you can't make it drink.
Exactly. Someone might be responsible for making a negative outcome more likely, but not necessarily responsible for the outcome itself, especially if other things were at play.
So it's not just about what someone did, but the context and how likely it was that their actions would lead to that specific result.
Yeah, that's key. This also has implications for the legal system when we're trying to figure out guilt or innocence.
Yeah, I can see how things get murky. If we can't say for sure that someone's actions caused a specific harm, How do we make fair judgments?
It's definitely a challenge. Probabilistic causation forces us to deal with degrees of certainty. We have to weigh the evidence very carefully, consider both how likely it is that someone's actions contributed to the harm and the possibility that there are other explanations.
So we're shifting from looking for a clear chain of events to evaluating the likelihood of different causal scenarios.
That's the idea. And this impacts public policy, too.
Oh, how so?
Well, if we accept that social interventions like policies aren't guaranteed to work every time, that changes how we approach policymaking, right?
Right, we can't expect every policy to be a perfect solution.
Exactly. It's more about nudging things in the right direction, increasing the chances of good outcomes.
So instead of aiming for guaranteed success, we focus on interventions that have a good chance of working, even if they won't work every single time.
Yes, and we need to use evaluation methods that can tell the difference between the effects of the policy and the effects of other things.
Right, because we can't be 100% sure about what's really causing what.
Exactly. Probabilistic causation is really a call for humility in how we approach the world. It reminds us that we don't always have all the answers.
But how do we make this probabilistic perspective more practical for everyday life? Is this just something for philosophers and scientists to worry about?
That's a great question, and it leads us perfectly into the last part of our deep dive. The good news is that anyone can apply the principles of probabilistic causation to their own decision-making.
Okay, so we're back, ready to wrap up our deep dive into probabilistic causation.
And I'm looking forward to giving our listeners some tools they can actually use, for navigating a world where cause and effect are rarely simple.
Exactly. Most of us aren't philosophers or scientists, but we still have to make decisions all the time based on how we think the world works.
Absolutely. So how can we bring this probabilistic lens into everyday life? One key takeaway is to really watch out for those confounding variables, those sneaky factors that can make it look like there's a causal link when there really isn't.
Right, like that classic example with ice cream sales and crime rates. It's not that ice cream causes crime, it's that hot weather makes both more likely.
Precisely. Recognizing those confounders can help us avoid jumping to conclusions about cause and effect. So instead of just assuming there's a direct connection, we should always ask ourselves, could there be something else driving this?
So a healthy dose of skepticism is key. Don't just take those correlations at face value. What other strategies can help us think more probabilistically?
Thinking in terms of probabilities, not absolutes. Instead of asking, will this action guarantee this result, try asking, how likely is it that this action will increase or decrease the chances of this result?
So it's not about all or nothing bets, it's about trying to tilt the odds in our favor.
Exactly. Like if you're thinking about starting a new exercise routine, don't get hung up on whether it guarantees you'll lose weight. Ask yourself, how likely is it that this routine, along with other healthy habits, will improve my chances of reaching my fitness goals?
That makes a lot of sense. It's about accepting that uncertainty is part of the equation, and then making choices that are aligned with our desired outcomes, even if we can't control those outcomes with absolute certainty.
Right. And this way of thinking, this probabilistic mindset, it's applicable to all kinds of decisions, from personal choices about your health or finances to professional decisions about investments or strategies.
It's about being comfortable with shades of gray,
Yeah.
recognizing that most of life's decisions involve navigating a web of probabilities, not just following a straight path to a guaranteed result.
Absolutely. And I think this perspective can also make us more understanding and compassionate, both towards ourselves and others.
Oh, interesting. How so?
Well, when we acknowledge that outcomes are often influenced by a bunch of different factors, some of which are outside our control, it fosters humility and empathy.
Instead of blaming ourselves or others for things that might have been largely due to chance, we can focus on understanding the factors at play and making choices that increase the likelihood of those positive outcomes.
Exactly. It's a shift from judgment to curiosity and compassion.
This has been such an insightful deep dive. Probabilistic causation, with its focus on probabilities and possibilities, really provides a powerful way to understand cause and effect in a world where certainty is often out of reach.
It encourages us to think more critically, avoid simplistic conclusions, and recognize that actions and events are often part of a complex web of interconnected factors that influence their likelihood.
It's a reminder to embrace uncertainty, hone our probabilistic reasoning skills, and make choices that align with our desired outcomes, even when we can't guarantee those outcomes with absolute certainty.
And in the end, I think this probabilistic perspective can help us navigate the complexities of life with more wisdom, humility, and compassion.
Thank you so much for joining us on this deep dive into probabilistic causation. We hope you've learned some valuable insights that will help you see the world with a more nuanced and discerning eye.
And remember, even in a world full of probabilities, your choices still matter. Keep exploring, keep questioning, and keep diving deeper into that fascinating interplay of cause and effect.
Until next time, stay curious and keep those perspectives open.